Okay, as all of you probably know, this is called the periodic table. It gets its name from an interesting story. The periodic table is credited for this Russian, Mendeleev, and he was not the first person to develop this periodic table. He was the second person. A geologist developed it before him, but he didn't publish. And in the scientific world, it's publish or perish. Mendeleev decided to publish it after he got the thing together. And what he did was he took all the available elements at the time and organized them. He put them in one long, one-dimensional stream by atomic mass. I'll talk about that today as well. And he noticed that some things, and he also knew the chemistry of each of those elements, basic chemistry, and he noticed that some of the chemistry started to repeat. So what he did is he cut that one long string every time the chemistry repeated and moved it down below it. So he ended up with 7 of these. And so you have columns of elements that have similar chemistry. Now, I'm going to later on in unit 4, I'm going to tell you why that's so. It has to do with valence electrons, the organization of those valence electrons, which are electrons on the outermost orbital. Okay, so this is what we have today. This is outdated. We have elements going all the way here, and that one is more correct. Okay, so let's talk about the organization now. Because it's two-dimensional, there are columns and rows. The columns are called groups. And every group has got a fancy name. You're going to have to know 4 of them. The first group is the first one, and that's called the alkali metals. So all the alkali metals have the same chemistry. They form the same charge when it forms an ion, the same level of stability, etc. Second group, well, this one's here. Second one's the alkali earth metals. Second from the right is the halogens. And the last one are the group called noble gases. Now, all the groups have names, but most people don't use those names. Most people use these 4. They're very common. Okay, most of the periodic table are metals. And not hydrogen. So if those are metals, what do you think those are? Non-metals. Now there's a transition group going from metals to nonmetals, and those are called metalloids. And that's on either side of that black squiggly line. Thank you for shutting the door. That's one of the cons of having a museum part of our complex here. So these guys here, wherever it touches the squiggly line, are metalloids. And those have the characteristics of metals and nonmetals. Okay, metals, they're shiny. Nonmetals, dull. Metals are malleable, means you can bend them, shape them. Nonmetals are brittle. Metals conduct electricity. Nonmetals don't conduct electricity. And these are the most common characteristics of metals and nonmetals. Now, metalloids can act like a metal, or it can act like a nonmetal. And it has to do with the charge. Okay, so what do we mean by that? If you apply a positive charge to a nonmetal, it'll conduct electricity. If it's negative, it won't. It's like a switch. Now, in 1947, let me back up 2 years. In 1945, one of the first computers were developed. They were the size of this room, and it was designed to track the flight of a cannon on a ship. It was this big, all vacuum tubes. There was another room almost this big to cool this room, because vacuum tubes put out a ton of heat. You can burn yourself if you touch a vacuum tube after it's been on for a while. Burn yourself, it's that hot. Now, all that's inefficiency, but it is what it is at the time, 1945. In 1947, Bell Labs invented something. And that's the modern AT&T, Bell Labs. Does anyone know what that is? I just told you the cons of that first computer, all the heat generating. Huh? Yeah. They took metalloids and devised something called a diode. And the diode is an electronic switch. And the reason why diodes work is because of metalloids. I have a hat that one of my students got me. It says, metalloids are cool. I always forget to bring it at the right time. But okay, so the diode, they use today, they use these a lot. And then from there, they went ahead and developed something called a transistor, which is more complicated than a diode. And then they started shrinking them. So now we have literally millions of transistors on a little chip. So everything now, I doubt there's anything that's not electronic related. And it's all because of metalloids. It's pretty cool. Okay. By the way, very few of my classes, I've been telling this story about Bell Labs for decades. Very few of my classes were able to mention what 1947 Bell Labs invented. Very few, maybe like 3 of all those years. Just accolades, what can I say? Okay, so let's go back to this grouping thing here. Now, how long have you been talking about this? The 8 minutes? This is how valuable that 8 minutes is. Remember I said the groups all had similar chemistry. Now let me give you a story, show you how valuable that information is. So I went to the doctor. The doctor said your blood pressure is too high. And he says, what kind of diet do you have? I said, well, I cook 99% of the time. I cook at home, and I belong to a gourmet group, and we get together. In fact, this Sunday is our next meeting, and we're making empanadas from scratch, of course. And he said, well, how much salt do you use? And I said, enough. Now, my problem is when I had COVID, my taste and smell like went away. So I have to put a ton of spices on stuff for me to really enjoy the dish. In fact, many of my friends have the same problem for the same reason. Okay, who remembers this is a hard one now. Who remembers the formula for table salt? Hmm?
Same. Same.
Table salt.
Well, it's
What's
sodium
it?
chloride.
What is it?
Sodium
Sodium chloride. Okay, let's look at this guy. The chloride part makes it salty tasting, not the Na part. So the doctor said, get rid of that salt in your diet. So I like to cook. I'm going, I don't think so. However, being a chemist, I said I can have a salt substitute. So let's look on the periodic table where sodium is located. It's right here. Oops. Okay, everything in that group, that alkali metal group, has the same properties. What is right under sodium?
Potassium.
Potassium. So what we do is we substitute potassium for the sodium. We still got the chloride there, which makes it salty, but we don't have the sodium in there. That's raising my blood pressure. Now, see how valuable that 8 minutes we spent on the periodic table is? Okay. Whenever we have a nuclear issue, we have a problem. One of the problems is strontium becomes, and iodine actually, become very radioactive to the point of being dangerous. So during Chernobyl let off a whole bunch of bad stuff, and it drifted across Europe, even into this country. It's a long way from Chernobyl. And what happened is all the strontium was part of the junk that gets thrown up there, part of the dirt and all that stuff. The strontium settled down, and it settled down in pastures and houses and everything else, but settled down into the pasture. Who lives in the pasture? Cows. And what do cows make? Milk. Okay. So what's going to happen is the cows eat irradiated strontium. It affects their milk. What's in milk that's good for you? Calcium. Notice where calcium is. It's right above strontium. Here's strontium. Calcium's right above it. So why is calcium important for us? Bones. What is made in the bone marrow? Blood cells. People that take in irradiated strontium typically develop leukemia. Again, it's related to the periodic table. It's really cool. One more example. The reason why, by the way, just FYI, the reason why iodine is susceptible during nuclear accidents, it has to do with your thyroid. Who's seen Chernobyl? Okay, remember at the very beginning, remember the woman nuclear scientist in the next town over? When the one scientist came to meet with her, they talked. When he left, she went to her secretary and gave her iodine pills. The reason she did is so that her system was saturated with iodine, because your thyroid takes in iodine. That's why when you buy table salt, some is ionized, some is not. And the reason is because of your thyroid. So what the deal is with the iodine tablets is to saturate your thyroid with the good iodine, so it's not going to take up any of the bad iodine that's floating around. By the way, Chernobyl is excellent. It's 98% scientifically accurate, but it's excellent. It shows a bunch of stuff with an old reactor. I mean, this is a really old one they were using. And what happens when politics gets involved? Not a pretty picture at all. And unfortunately, it's a true story. That's the unfortunate part. Okay, one more example. When someone gets a new body part, like a joint, what is it usually made out of? Titanium, what else?
Screws, nails?
Screws and all that stuff, yeah. Something non-metal.
Carbon.
A carbon substitute.
Oh,
Find carbon on the periodic table? Right here. And what's underneath carbon?
Silicone?
Silicone. That's why a lot of stuff they put in your body is made out of silicone, because it's underneath carbon, and carbon is the building block of our bodies. So again, it has to do with groups on the periodic table. Okay, so let's talk more about this now. Let's see, we've got okay, when you look on the periodic table, let's take carbon. Now, carbon's got two numbers, a symbol, and sometimes a name, depending on what periodic table you have. Yours doesn't have the name on it. I'm sure one in your lab packet does. It's just that in 1A, they expect you to know these symbols and what the name is. So that's why this is the official departmental's periodic table, except not mine. Mine has the names in. Okay, let's look at carbon. Carbon's got two numbers, an integer and a decimal number. And the symbol for carbon is C. Okay, so let's blow this up.
Question,
Yeah,
since I've never heard of halogens before, what is that? Halogens.
cal,
Halogens, it's next to noble gas, so it's not a gas, but it's something before it becomes a gas? Is that what a halogen is?
halogen is just a group of chemicals that have similar chemical
Oh.
properties. They are gases, but they're diatomic gases, meaning they have to have two of them together. So it's like Cl2, Br2, I2. Those are called, there's 7 of them that are gases.
And then you two to become a halogen.
No, it needs 2 to become a gas.
Oh, it needs two to become gas.
Because chlorine by itself is all over the place. It's in food, it's in pesticides, it's in pools. I mean, it's all over the place. And it's also a gas. Okay, so let's look at okay, let's talk about the numbers now. The integer is called the atomic number. And that's the same as the number of protons. Now, there are 3 subatomic particles. Electron, protons, neutrons. Protons have a charge of +1. Electrons have a charge of -1. And neutrons have no charge. These 2 are in the nucleus. Electrons are around the nucleus. Except for one exception. The neutron. The neutron is made up of a proton and an electron in one body. So you can say there are electrons in the nucleus as well, because they're buried inside of a neutron. Most books don't say that. But if you study nuclear chemistry, that's where a beta particle comes from, is inside the nucleus. Beta particle is an electron. Okay, so this is the number of protons. So carbon has 6. Okay. That's a symbol for carbon. Now the symbols are either 1 letter or 2 letters. Now it's absolutely important to write them correctly. COCO. On your left is cobalt. On your right is carbon monoxide. They're both COs. So if the element has 2 letters, the first letter is uppercase, the second letter is lowercase. No exceptions. For example, this is why. Okay. All right, carbon, some of the older elements are 1 letter. And then later they had some problems, like calcium is Ca, cobalt is Co. So all of a sudden the C's are starting to come in. So that's why they came up with the second letter. But all the old elements, the elements that were discovered a long time ago, like thousands of years ago, only have 1 letter. Okay. Now, that guy, we're going to be using this decimal number a lot in this class. And the fancy name for it is called atomic mass or molar mass. The difference between the atomic and the molar is if there's just 1 element in the formula, it's atomic mass. Like here, only carbon, just the one. If it's a molecule like CO2, then it's molar mass because it's an additional atomic masses added up. So molar mass is so the sum of the atomic masses in a molecule equals the molar mass. Okay. Now, um, okay, we are going to do this today. Yeah.
I was gonna be in that. We've done it first. It's trouble. It's terrible. Well, it's like that. We know. I was just. Yay. Some of all of our. Really? The whole. First song. That's same today. About this. The one where she says no, it's me, it's just one of her one of them. Yeah. Don't give them a your father. The only one that's technically. Yeah. I think it's like, it's like, it's just really simple time. Yeah, it's still work, but that's. Because we're just keep there. But. We have to charge it to the max with a low battery. I just saw it.
Yeah.
Oh.
I don't travel without. The bad news about old laptops. Okay. Let's. Now, on the periodic table, again, there are two numbers. There's an integer and a decimal number. Now, the decimal number involves something called an isotope. Now, what is an isotope? The character of an atom, in other words, the chemistry, is determined by a number of things. One is number of electrons, and specifically the electrons in the outermost orbital. Those are called valence electrons. It's also determined by protons. Because in a neutral atom, protons equals electrons, because the net charge is 0. So if you get these electrons running around with a -1 charge, say we had 6 of them, like for carbon, we have to have 6 protons to balance those 6 negative charges. So the net charge is 0. The other the non-chemistry are the number of neutrons. So you're going to have as many neutrons as you want. It doesn't change the chemistry because the valence electrons, the electron in outer orbital again, determine the chemistry, not the neutrons. So let's look at carbon, for example. So this is the number of protons. And in a neutral atom only, the number of electrons equals the number of protons, because we have to have a net charge of 0. Okay. So the isotope, we probably heard this term before. An isotope has the same number of protons different numbers of neutrons. Let me give you an example. There's carbon 12 and carbon 14. Very common isotopes. Now, the bottom number is the number of protons, right? Number of protons determines what element the name is. Nothing else, only protons, no exceptions. So if we had a nuclear reaction where we increase the number of protons, called beta decay, happens all the time, the element changes because the number of protons goes up by 1. So it's now a new element. Or transmutated. That's what transmutation means. You're changing the number of protons. Now, alchemists 500, 600 years ago were trying to do that. They wanted to change cheap metals like lead into expensive metals like gold. Never accomplished it. We do that all the time today. It's very expensive, but we do it all the time. They didn't have cyclotrons in those days. We have these cyclotrons big time. Okay. So the difference between carbon-12 and carbon-14 is this top number. That's the sum of the protons and neutrons. So carbon-12 has 6 protons because it's carbon. So how many neutrons does it have? Carbon-12. 6 plus what is 12? 6. That means it's got 6 protons, 6 neutrons. Carbon-14 has 6 protons. How many neutrons? 8. So carbon-12 and carbon-14 are isotopes of one another because the number of neutrons is not equal. Number of protons is equal because we're calling it carbon. Carbon only has 6 protons. Okay, does that make sense? Now, you always have the bigger number on top, smaller number on the bottom. Okay, except for the periodic table. Periodic table has it opposite. Big number on the bottom, little number on top. So other than the periodic table, whenever you write an element, you're going to have the isotope number on top and the protein number on the bottom. Okay, now again, the only exception is periodic table, and it's a big exception. So periodic tables all over the place. But they standardized this a long time ago. They have protons on the top, isotope on the bottom. Now the atomic mass is also the isotope, because atomic mass includes neutrons and protons. Notice it's 12.01. It's a decimal. Can you have part of a neutron? Nope. So why is it a decimal? Let me give you this simple analogy. If I've got a bowl of oranges, 10 oranges in there, and each orange depends on its mass of the orange, depends on how big it is. Still an orange, right? Still an orange. How big is it? How big's the skin on it? How much juice is in there? All those are variables that determine its mass. So if I weighed one of the oranges, would the mass of the bowl be 10 times that? No, because each orange is still an orange, but it doesn't have the same characteristics. It's got different mass, different amounts of juice, all this other stuff. So if I weighed the big bowl and divided by 10, I would get a decimal number. That's the same thing going on with the decimal number in the periodic table. It's an average of all the isotopes for carbon. So this 12.0 for carbon is the average of the isotopes of carbon. Carbon 14, carbon 12, carbon 11, carbon 13, all those together is 12.01. Okay, notice of all the isotopes, let's say there's carbon 12, carbon 14, carbon 11, carbon 9. What have we left off? Okay. So if the average of all those carbons is 12.01, what's the most common isotope of carbon? 12, because it's closest 12. That's the most common one. But there are others around. If there were not others around, we would have an integer. For example, over there, look at uranium on the very bottom. Uranium is 92. Next one is neptunium. Okay, notice this in parentheses. Some of these are in parentheses, and it's just one of them. That's one of them. Most periodic tables reflect this. The parentheses are integers. For example, there. Notice this parentheses numbers are all. That's because those are made in a cyclotron or they're made in a bomb. And when that happens, only the most stable ones are around. That means there's only one isotope. That's why there's no decimals left. Okay, so so there are two ways to name an element. One is with a symbol, like here, with the two numbers, the top number being a combination of protons plus neutrons, the bottom number is number of protons, or carbon 12. So in this worksheet, you're going to be doing some of both. Okay, so we are going to fill in the empty spaces. Okay, so boron is, the atomic number is 5. So how many protons does boron have? 5. Because the bottom number says 5, the number of protons, okay? How many neutrons does boron have? 6, because 5 plus 6 is 11. Okay, so we're going to name this boron 11. What's the atomic number for boron? 5. Oops. Remember, atomic number and protons are always equal. So that means we have 5 protons as well. 6 neutrons. So the atomic mass is going to be P plus N. So we have 6 neutrons, 5 protons. 5 plus 6 is 11. So the atomic mass of that specific isotope is 11, no decimals. Now, if you go to the periodic table and look at boron, it's got a decimal number there as well. That's the average. This is specifically one of those that's used in the average. That's why there's no decimal point. Okay, number of electrons. Now these are all neutral. Now, if I tell you they're ions, that changes the picture. But unless I tell you that, consider them neutral. So if it's got a neutral charge, how many electrons do we have? 5. Okay, so when it's neutral, protons and electrons are equal because the charges have to balance. Okay,
I have a question, can we go over that part? So like protons are neutral, how do I know if it's neutral? Because of the 6 neutrons?
because I'm telling you all
Oh.
these are neutral. I have to tell you.
Oh, okay. I was like,
And then I have one very similar to this on ions, and we'll talk about that later. And then I have to say they're ions.
thank you. Okay.
The other way to tell is if the this here had a charge, if B had a charge, plus or minus, then you know it's an ion. If there's no charge, it means it's neutral. That makes sense?
You said negative, minus?
If there's a minus charge or a positive charge, it's going to be an ion. Huh? Yeah. Salt, sodium chloride. There's a whole bunch of ions in the world. Ions are more stable than non-ions. That's why there's more ions in the universe than. Okay, so this is what I want you to do. We have 20 minutes or so left. I want you to work on this. You can work in groups if you like. And if you'd like to look up the answers, go to Canvas, Files, Unit 2, and you should see one. And on the second page of it are going to be all the answers. Okay? Want me to do one more?
Yes.
Let's do empty spaces on what?
The opposites that we fill in, so I would.
Check if I got everything right.
Almost. You have to put the like boron -11, sodium -23. Now, this number here should be the same as the upper number here.
Gotcha,
So that should be 2411,
gotcha. Yeah,
because we have 11 and 13 is 24. So 24 in the top.
gotcha. I think I know everything wrong. I was looking at the periodic table by charts and I just.
Yeah,
Yeah,
yeah, you're not gonna, because the periodic table has the average.
yeah.
This is just one of those isotopes taking part in the average.
Mhm. Yeah, I think that's what I did in the average. So,
You understand, right?
yeah, I understand.
Let's see.